To close out the session, we have Ningning Shi presenting a variant of algebraic effects that admits efficient implementation.
Hello everyone, I'm Ningning. I'm going to present our work, Effect Handlers Evidently. Hello everyone. In this work, we show that we can elaborate algebraic effects by evidence passing to polymorphic lambda calculus. This gives new semantics of algebraic effects. In particular, there is no need for a special runtime system for implementations. This can be extremely useful if you want to compile algebraic effects to languages like C. Moreover, we show that with evidence passing, such implementation can be quite efficient. Before we go to the technical details, let's start with an overview of algebraic effects. Algebraic effects and the extension with handlers are a powerful way to incorporate effects in programming languages. To understand how it works, we start with a typical example of the reader effect. On the left-hand side, we define a simple effect, reader, which has a single operation, ask. The type of ask says that you can call ask by providing a unit argument. It will then return you an integer. Now we can already start using ask. The expression below simply calls ask twice and returns the sum. However, we still don't know how it would evaluate. The semantics of effects is given by effect handlers, where handlers provide operation implementations. We handle an expression by wrapping it in a lambda which takes a unit. In our example, we use x to denote the operation argument, in this case, unit. The extra argument k is implicitly provided by the system, which denotes the resumption, that is, how to resume the computation when an operation is performed. In this case, we always resume with 1. When the first ask is performed, the handler returns 1, and we have 1 plus perform ask unit. Then the second ask is performed, and we have 1 plus 1, which gives the result 2. One remarkable feature of algebraic effects is the decoupling of effects and the implementation of effects. In particular, we can use the same handler to handle a different computation, or we can easily use a different handler to handle the same computation. In summary, algebraic effects provide a useful way to encode composable and modular computational effects by having effects which define a family of operations separately from handlers, which give semantics to operations. We have seen the example of reader, and we refer to our paper for more complicated examples. However, it is non-trivial to support algebraic effects in real-world programming languages. We demonstrate the issue with this example. This code has 3 handlers, followed by an expression which simply calls ask twice, as we have seen before. The 3 handlers are a reader handler, an ink handler, which increases the computation result by 1, and an exception handler, which returns a default value 3 if the computation fails. As before, since the reader always returns 1, we expect the answer to be 2. Now, let's take a closer look at how this expression evaluates. We first evaluate the reader handler. Now we need to remember that we have a reader handler available in the evaluation context, since later we may need to use the handler to handle certain operations. In a similar way, we evaluate the ink handler and the exception handler. We then hit the first ask, but we don't know how to handle it. Thus, we yield up to the evaluation context and hope to find a reader handler. The innermost handler is an exception handler, which is not useful in this case. We keep going up and find an ink handler, which is again not useful in this case. Finally, we reach a reader handler, which says that we should always resume with integer 1. Now we need to resume and go back to where the operation is handled. And this is where we hit the second ask. Now we need to repeat the whole process again by first yielding up and then resuming. As you may have noticed, implementing algebraic effects this way requires special runtime support to yield up, to capture the resumption, and to resume. This is very difficult to add to existing programming languages. Moreover, it is very inefficient. To support two asks, we have yield up and resumed twice. It can be more time-consuming if the handler stack is even larger. Hence, the goal of our work is to have composable, modular, efficient, and easy-to-implement computational effects. To this end, we present new semantics of algebraic effects in terms of polymorphic lambda calculus by first introducing an intermediate evidence calculus. We can then elaborate polymorphic algebraic effects via evidence passing translation to the evidence calculus. This turns out to be surprisingly tricky to get right. In particular, the coherence of evidence translation turns out to only be preserved under scoped resumptions. Finally, we define a monadic multi-prompt translation from the evidence calculus to the polymorphic lambda calculus. Combining these two translations, we get an implementation of algebraic effects upon plain polymorphic lambda calculus and thus requires no special runtime support. We have proved awesomeness and coherence of the translation. It also turns out that doing evidence translation does not only get rid of special runtime system, but also allows us to implement algebraic effects more efficiently, especially for tail resumptive operations. In the rest of the talk, we first go through the meaning of the scoped resumptions and then discuss these two translations. To understand the restriction of scoped resumptions, let's consider this example. Here we have two handlers, h1 and heval, that wraps the expression E. The whole result is then given to F. The definition of E performs three operations: ask, eval, and ask. The handler h1 is a reader handler which handles ask by always resuming with 1. A reasonable expectation now is that these two asks in E would both return 1. However, we show that while the first ask, as expected, gives back 1, the second ask gives back a different number 2. How is that possible? We define the eval handler in a way that, instead of resuming, it directly returns the resumption k. F then gets the resumption and applies the resumption under a different handler h2, which handles ask by returning 2 instead. Note in this example, k is captured under a handler context with h1 and is resumed under a different handler with h2. This is very powerful, perhaps too powerful, as it can interfere with the ability to reason about the program. We define the notion of scoped resumptions as a restriction of general effect handlers, where resumptions can only be applied in the very scope of their original handler context. Thus, the previous example is rejected under scoped resumptions. We believe all important effect handlers can be written with scoped resumptions, including complicated examples like async or concurrent scheduling. The previous example can also be rewritten to pass the restriction. In this work, we focus on the evidence translation and use a dynamic check in our formalism. In the paper, we also show several designs on how to check this property statically. Using scoped resumptions, we define the evidence passing translation. The key idea of evidence passing is that a vector of handlers is passed down as an implicit parameter, similar to the dictionary translation in Haskell for type classes. To understand how evidence passing works, we re-evaluate the previous example using the evidence passing semantics. As before, we first evaluate the reader handler. This time, we create a fresh unique marker represented as M1 to denote this particular reader handler. We call the pair of the marker and the handler an evidence, and we pass the evidence down as we evaluate. We then evaluate the ink handler by creating another fresh unique marker M2 and pass the new evidence along with the existing reader evidence. That is, we now have an evidence vector. We denote an evidence vector using the letter W. We do the same for the exception handler and get one more evidence. Now we hit the first ask operation. This time, we first inspect the evidence vector. From the evidence vector, we find the reader handler that is supposed to handle this operation has marker M1. We can then yield up, but in this case, finding the correct handler can be much faster than before because we only need to compare the markers. Actually, the evaluation can be even faster. That is, we don't need to yield up at all. Because from the evidence vector, we do not only know the marker of the handler, but we have the handler itself available. From the handler implementation, we know that the reader handler has a tail-resumptive implementation. Therefore, we can evaluate the handler in place and get a result 1 as the result of ask, and keep evaluating. We can then hit the second ask and get another one. Compared to the previous evaluation, this time the evaluation is a straight line, which means that it does not change the control flow at all. This is thus much more efficient than the previous one. To make such evaluation strategies possible, we have proved the following theorem. The theorem essentially states that when performing an operation of effect L, the handler we find in the evidence vector W, which is W.L, is exactly the innermost handler for that operation in the dynamic evaluation context, which is MH. Thus, with evidence passing, we significantly improved the efficiency of algebraic effects. In particular, tail-resumptive operations can evaluate in place. This optimization enables truly efficient effect operations at a cost similar to a virtual method call. Non-tail-resumptive operations still need to yield up, but from the evidence vector, we can locally decide which marker to yield to, which is still more efficient than finding the handler dynamically. Hello, everyone. Based upon evidence passing, we can then implement handlers using multi-prompt delimited continuations. Specifically, given evidence MH, we can directly yield to a specific prompt N. Moreover, since the evidence provides the handler implementation directly, it is no longer needed in the context. Such translation is very important, as it provides the missing link between traditional implementations based on dynamic search for the handlers and implementations of lexical effect handlers using multi-prompt delimited control. Specifically, we define a multi-prompt translation from the evidence language into standard polymorphic lambda calculus, where the monad implements the multi-prompt semantics. Now, no special runtime system is needed anymore, and we can generate code directly for languages like C or WebAssembly. Moreover, with a standard backend, advanced compilation strategies can be used, for example, compilation-guided reference counting. Hello, everyone. We summarize all calculi and meta theory in our paper using this figure. We have a polymorphic algebraic effect calculus, system FE. We can erase the types in system FE and get to an untyped algebraic effect calculus, system lambda E. Also, we can do an evidence passing translation to a polymorphic evidence calculus, system FEV. Finally, we show that system FEV can use the multi-prompt translation and translate to a polymorphic lambda calculus, system FV. With both translations available, we get an implementation of polymorphic algebraic effects in terms of polymorphic lambda calculus. Hello, everyone. Please read our paper for more details. Moreover, we have provided an implementation of the evidence passing translation in the Coca programming language, and initial benchmark results are very promising. Finally, we present a Haskell library of effect handlers based on the technique described here. We encourage interested people to read our Haskell paper or watch the talk for more details. That's all. Thank you for listening.
Thanks, Ning Ning. In either time band, you should see a Q&A link appear in Clouder, which you can click to video chat with at least one of the authors of this paper. And that's it for this session.